So this is the section 19.3 lesson video for honors chemistry, and as always, if you want all my videos in one place, just subscribe to my channel. Alright, so section 19.3, we're going to talk about the strengths of acids and bases. Now we touched on this a little bit when we talked about electrolytes, so now we're going to dive back into it. So in general, strong acids completely dissociate in aqueous solutions, whereas weak acids only slightly ionize. So in other words, a strong acid, all the particles are going to break up, pretty much all of them. So if you look, all the particles have broken up. Whereas a weak acid, most of them, if you look, have stayed together. But there are a couple that have broken up. Alright, so a strong acid would be a strong electrolyte because it can conduct electricity well because of all those ions that can move. Whereas a weak acid would be a weak electrolyte. So the strong acids that you need to know, and you just really need to memorize this list because these are the strong acids. If it's not on this list, it's a weak acid. So the strong acids are HCl, HNO3, H2SO4, HBr, HI, HClO3, and HClO4. So just make sure you learn that list so you know what's strong and what's weak. So, an acid dissociation constant. So if you watched the previous lesson videos, you know we went over Kw, which was water. So Ka, the A stands for acids. The acid dissociation constant is the ratio of the concentration of dissolved ions to the concentration of undissolved acids. Now there's lots of different K values and they all work the same way. It's the products over the reactants, like the concentrations of the products over the reactants. Or if you get into other things, it could be the pressure, the partial pressures. So here's just a reaction of an acid in water, and it breaks up into, of course, HNO3 plus and NO2 minus because that acid is going to give its hydrogen to water. And so when we write the Ka value, we write our product concentrations over our reactant concentrations. But you may be wondering, well, where is water? When you're doing a K value, any K value, be it Ka, Kb, Kw, any of the other Ks you may learn if you take AP Chem, any pure solids or liquids, in our case H2O, is not included in the K value because K deals with concentration. You can't make more concentrated water that has more concentration of water than other water. That doesn't make any sense. So the concentration of pure solids and liquids can't change, so we leave them out of the K value. So the Ka value indicates the amount of ionized particles, so a weak acid has a small Ka and a strong acid has a large Ka. So remember, the K value is products over reactants, and I'm going to go back real quick. So it's products over reactants. The more that break apart, the stronger the acid. So if this part is bigger, you're going to have a large K. If your original acid that did not break up is bigger, because it's in the denominator, you're going to have a small K, so that represents a weak acid. Alright, so the larger the Ka, the stronger the acid is. So bases. Strong bases fully ionize or dissociate in aqueous solution, and weak bases only partially ionize. So again, here's a list of your strong bases: NaOH, KOH, LiOH, RbOH, CSOH, CaOH2, SrOH2, and BaOH2. Whoop, I need to make those parentheses big again. Oh well, I'll do that later. So the most common weak base that we'll use in here is NH3. Now there are a lot of other weak bases, but that one you may just want to remember because it doesn't have OH on it, so sometimes y'all tend to forget about that one. Alright, so let's talk about a Kb value. So Ka is of course your acid dissociation constant. Kb is your base dissociation constant, but it works the same way. Okay, so we have a base. I picked NH3 in water. And so what's going to happen is water is going to give one of its hydrogens to the base. Remember, we talked about the proton donor and acceptor thing. So it becomes NH4 plus and OH minus. So that's what makes NH3 basic, is the fact that it makes that OH minus from the water. So remember, it's products over reactants, but we're going to leave out water. So we do the concentration of our two products over the concentration of our reactant. Now, the larger the Kb value, the stronger the base, because of course the larger the number on top, the more ions that have been formed from that base. Now, a lot of times in here, I'm going to give you an acid or base where you don't know the formula, but it doesn't matter what it is. You can just use the generic formula for acids and bases because we don't need to do anything with molar mass. So for acids, the generic formula I like to use is HA yields H plus and A minus because we know an acid is going to lose its hydrogen. So So HA yields H plus A minus is, I like to use that one because it just discounts water completely because we don't need water in the equation anyway. However, you could do HA plus H2O yields H3O plus A minus. Just make sure to leave water out because remember we said H plus and H3O plus can be used interchangeably. So the generic formula for a base would be B for base, of course, and we add water. Now for base, you kind of do need water in the formula because otherwise where does the OH come from? So the base is going to gain one of the hydrogens from water and become BH plus, and then water will be left with OH minus. And so remember, we don't put water in, so it's BH plus times OH minus over the original concentration of the base. So how do we use these things? Well, I'm going to teach you something new called an ice chart. So this is an example of what a problem might look like. For 0.1 molar solution of ethanoic acid, it's only partially ionized. From measurements of the pH of the solution, H plus is determined to be 1.34 times 10 to the negative 3 molar. What is the acid dissociation constant, or Ka, of ethanoic acid? So you may be thinking, I don't even know the formula for ethanoic acid. Well, it doesn't matter. We know the generic formula for acid, and our reaction for acid is HA yields H plus A minus. So it doesn't matter whether you know the formula for ethanoic acid or not. It makes no difference. All right, so we set up what's called an ice chart. So it's ICE. And so I stands for initial, C stands for change, and E stands for equilibrium. All right, so we have initial, change, and equilibrium. So if we read, it says a 0.1 molar solution of ethanoic acid is only partially ionized, period. So that means I am only starting with 0.1 molar ethanoic acid. So that is my initial. So ethanoic acid is my HA, that is my acid. So I'm going to put 0.1 molar right here. Now, in our question that it gives us, it doesn't say anything about starting with H plus or A minus. And if you move on to other classes, you'll get to where sometimes you may have one of your products present also. But in here, it just says we're starting with ethanoic acid, so I'm going to assume that that means we're starting with 0 of our product. Unless it tells me I'm starting with some, we assume 0. Alright, so then it says, from measurements of the pH of this solution, H plus is determined to be 1.34 times 10 to the negative 3 molar. Alright, so where do we put that, and why can't we just go ahead and plug into Ka right now? Because we have an H plus, an A minus, and an HA. Well, when you plug into your K values, you have to use equilibrium amounts. You can't use initial amounts. So until we get 3 numbers at the bottom, we can't plug into our K formula. So it says they measure the pH. If they tell you they measure the pH, or if they just tell you what H plus ends up being, that is your equilibrium amount. Alright, so you're just going to have to kind of remember that. Sometimes it'll say like the student waits until it reaches equilibrium, but a lot of times it'll just go ahead and jump right in and say this is what H plus is. Alright, so that's our equilibrium. So you have to think, every time an HA breaks up, you're going to get one H and one A. So if 2 HAs break up, you're going to get 2 H's and 2 A's. Well, we got 1.34 times 10 to the negative 3 H's, so how many A's are we going to get? The same amount. Okay, it's all about the stoichiometry of the problem. So since H and A are 1 to 1, that means they always have to be the same amount. Now if A had for some reason had a 2 in front of it, I would have had to multiply that number by 2. Alright, so next, what are we missing? Well, we still don't know equilibrium for this, and our whole change row is blank. So where do we get the change? Well, the change is going to seem like a waste of time for our types of problems because we're doing what I call the newborn baby of ice charts, as in we're doing the easiest ones possible. So, you know, it's going to seem like a waste, but just make sure you learn it because when you get to the more difficult ice charts, if you have a good foundation, it's so much easier. So how do we get from 0 to 1.3 times 10 to the negative 3? Well, we have to add 1.34 times 10 to the negative 3. And the same thing happens for A minus. Because when you're using an ice chart, you're following down your column. So see how 0 plus 1.3 times 10 to the negative 3 equals 1.34 times 10 to the negative 3? Now, every time we make an H and an A minus, we have to destroy an HA because it has to break apart. So if I make an H and an A, I lost an HA. If I make 2 H's and 2 A's, I lost 2 HA's. Well, I made this many H's and A's. So that means I have to subtract that amount from my reactants, because you have to think in the reaction, we're going from reactants to products. So every time I make a product, I'm losing reactants. Now again, because everything is 1 to 1, I'm just going to plug in the same number. But say HA had a 2 in front, then I would have to alter my values from there. Alright, so how do we get this equilibrium? Well, we just follow our subtraction. 0.1 minus 1.34 times 10 to the negative 3. So I just subtract that in my calculator. And so when you do that, you end up getting 0.099 molar. Alright, so now I have my 3 values, so I just plug in. So remember, we said Ka is our H plus times our A minus over our HA. So then I just plug in. So my H is 1.34 times 10 to the negative 3 molar. My A is also 1.34 times 10 to the negative 3 molar. And my HA is 0.099 molar. Now, if you're trying to do units, you may notice 2 of the molarities would cancel, so you should be left with molarity, but remember, K values have no units. So just discount any units. So once I solve, I get 1.8 times 10 to the negative 5. Alright, and so it's all about just plugging into that ice chart. Like I said, we're going to do the newborn baby of the ice charts, the easiest ones possible. But they do get harder as you move on, where you have to do quadratic formula and all that kind of good stuff. Alright, so let's look at another one, because a lot of times the first one just confuses everybody. So maybe don't try the second one on your own yet. Maybe just watch me do the second one also. Then you'll start seeing the pattern and it'll make a lot more sense. This is just me showing all my work. Alright, so let's look at the second one together. Like I said, maybe try the third one on your own. Alright, so let me go ahead and put my page so I got all my math answers. Alright, so it says, in a 0.1 molar solution of methanoic acid, H plus equals 4.2 times 10 to the negative 3 molar. Calculate Ka. Okay, so again, we're dealing with an acid, so even though you may not know the formula for methanoic acid, we're going to use our generic reaction. Alright, and so we set up our ice chart. So my original initial amount of my methanoic acid is 0.1 molar. Now again, it doesn't tell me that I'm starting with anything else. Like sometimes it will, like it might say you have 0.1 molar acetic acid mixed with some sodium acetate, like a 0.1 molar sodium acetate solution. And then you actually have some of your HA and your A minus, but we're not going to do that in here. Remember, we're on the newborn baby, so we're on the easy ice charts. So we're going to start with 0 of both of our products. So it tells me H plus equals this. So remember, once you know what H plus or pH is, that is automatically your equilibrium. So I'm going to bring my 4.2 right here. And because H plus and A minus are 1 to 1, I'm going to put the same number under A minus. See how once you watch it the second time, it like starts to be a little easier. Like it's like, oh, it's just a pattern. Alright, so how do we get from 0 to 4.2 times 10 to the negative 3? Well, we had to add 4.2 times 10 to the negative 3 for both of them. But remember, if you added that much to the products, what do you do to the reactants? You have to subtract that much. So minus 4.2 times 10 to the negative 3 from my reactants. And so then to get this equilibrium value, you just do 0.1 minus that number. So when I did that, I got 0.0998. And so then once you have your 3 equilibrium values, you just plug into your Ka formula. So it's H plus times A minus over HA, just as a reminder. And so then we just plug in. So our H plus is 4.2 times 10 to the negative 3 molar. Our A minus is also 4.2 times 10 to the negative 3 molar. And my HA concentration is 0.0998 molar. Again, no units on our K value. So once I solved, I got 1.77 times 10 to the negative 4. Yep. Okay? So usually after people see it the second time, they're kind of like, oh, this isn't that bad. It's usually the first time that everybody's like, oh my God, what are you doing? Okay, so now that you've seen it a second time, maybe pause the video and try this third one. And then, of course, we'll do it together. So just pause it. You have this to kind of look at to tell you what to do. and the previous one. All right, pause it, try it, and we're doing it together now. So it says in a 0.2 molar solution of a monoprotic weak acid. So this one, it doesn't even tell me what the acid is, but it doesn't matter. It tells me it's monoprotic, which means one hydrogen. So I can use my generic formula. Again, if you move on, you'll get to diprotic and triprotic and how you have to do those differently. You kind of have to remove one H at a time. It gets kind of difficult, but awesome at the same time if you like doing ice charts, which I personally do. So anyway, we're going to start with our generic formula. So HA yields H plus A minus, and we set up our ice. So it says we're starting with a 0.2 molar solution of our monoprotic acid. And then again in here, because we're doing newborn baby ice charts, we're starting with 0 of our products. And then it tells me that H plus is 9.86 times 10 to the negative 4 molar. So I'm going to plug that down here for my equilibrium. And because H plus and A minus are 1 to 1, I'm going to put the same number for A minus. And then, how did I get from 0 to 9.8 times 10 to the negative 4, 9.86 times 10 to the negative 4? I just added 9.86 times 10 to the negative 4. Alright, and so if I add that much to products, what happened to reactants? Well, I had to subtract that much. Because every time I form products, I'm destroying reactants. Ooh, my 6 kind of got a little crazy here. Okay, so I have to do 0.2 minus the 9.86 times 10 to the negative 4, and that changes that number to 0.199 molar. Alright, and so now that I have my 3 equilibrium values, I can just plug in. I'm not going to rewrite the formula again because it's literally right here. So I plug in my H plus, which is 9.86 times 10 to the negative 4 molar. I plug in my A minus, 9.86 times 10 to the negative 4 molar. And then I plug in my HA, which is 0.199 molar. Remember, no units for K values, and when I solved, I got 4.89 times 10 to the negative 6. Okay, so the important thing to realize is some of y'all, you're probably already seeing the pattern for the newborn baby ice charts. And that is, well, aren't we just doing this number times itself on top divided by this number minus this number? Well, yes, that is exactly what we're doing. So you may think, well, why can't I just do it that way? Well, I want you to know how to do an ice chart because when you move on to college or if you take AP Chem, once you start changing the ice charts and you have coefficients or you have more than one starting amount or you have unknowns where you're doing plus x and minus x and plus 2x and then you're having to do powers that we haven't done in here, it's so much easier if you can set up a basic ice chart. Okay, so like in my class, if this is on a test or quiz, you have to show your ice chart to get credit. Okay, like I don't actually really care that much if you can calculate the answer. I mean, you're going to have to get the answer too. But I make you show the ice chart because I want to give you that foundation for if you move on. Alright, so let's move on, speaking of moving on. Alright. So let's knock out that section assessment, which for some reason randomly starts at number 3. Alright, so it says compare a strong acid and a weak acid in terms of the acid dissociation constant. Well, remember, acid dissociation constant, your Ka, is H plus times A minus over HA. Remember, our reaction is HA yields H plus plus A minus. Okay, so it's products over reactants. So a strong acid would have more ions because remember, a strong acid breaks up more. So if you have more ions, that's a bigger numerator, so it would be a bigger number. A weak acid, on the other hand, has more that did not break up. Well, because your acid is in the denominator, that would be a lower number. So we can just say a strong acid has a larger Ka than a weak acid. Okay, so a strong acid has a larger Ka than a weak acid. So, hopefully newborn baby ice charts weren't too bad. They do get worse if you do move on, just saying, once you gotta use that quadratic formula and stuff. But we're just doing the newborn baby ones, but make sure you understand them, alright, and know the difference in strong and weak acid.